You all seem to like the trick of how to get a dross-free cut on a handheld plasma cutter, and I asked a simple question in that video if y'all want to see it on a CNC table. Let's get into it. Get out of here. Now I want to first give the disclosure that I am but a humble welder, and I am still learning this stuff to this day. I'm still learning different things about the equipment that I've had. I used to run a different table. Right now I've got a fast cut CNC icon table. This is a 5x5 CNC table. I had something a lot smaller beforehand. It was a 4x3 Langmuir Systems CNC table. It's a lot more of a hobby shop kind of version of what we got going on that you see behind me. Now there's a lot of things to consider when it comes to CNC plasma, but plasma specifically, guys, you got to go see these other videos. We have a great video on the ThermaCut Extra Fire and its capabilities, which is the plasma cutter that we're going to be running today, as well as how to troubleshoot your normal plasma cutting issues. There's a great video on that we did recently, and of course the video we just recently did about getting clean cuts with your plasma cutter. All these things are going to tie in together in this episode as we take bits and pieces from each one of those episodes and apply it here on the CNC table. Now CNC plasma cutting compared to hand plasma cutting has the same needs, right? You need air, you need enough of it, it needs to be dry, you need to have right consumables for the right thickness of metal, and you need to be working on the same travel speed. That's what we're going to go over in the same things today. With the CNC table, the whole point of it is to be able to run non-stop, clean, straight, beautiful cuts forever, all the time. So for the Extra Fire, for example, I've got the 85. That's right, you're going to have to be looking into these manuals now. I've got the Extra Fire 85 HD, and it's going to say that you need 6 CFM at 101.5 PSI. So we need at least that. You'll see that I've got that 60-gallon DeWalt outside, 11.5 CFM, so we're good, and that's at 90 PSI. So I used to have this Husky here. This Husky was what I was running before when I was running the Everlast Power Plasma 52i. The Everlast Power Plasma 52i says it only needs 5 CFM or better with a 25-gallon tank at 72 to 75 PSI. Well, that Husky here, if we look at it, it has that. It has 5.1, so even better, and at 90, so even better. We're good to go as far as running that 52i. Of course, it doesn't have the same amperage as this Extra Fire 85 HD has. It's not going to be able to cut as fast, even at its max. And then you're going to have to equate to duty cycle and things like that. But as far as compressor, this is fine, right? This is the compressor you need. I tried running the 27-gallon compressor on here, and it would cut for a while, and then you'll notice the cut quality start to get worse and worse and worse, more and more dross on the ends of the cuts until the plasma cutter will eventually just read an error code because it doesn't have enough gas to cut with. So not only do you need all this to consider whenever you're trying to figure out what plasma cutter you're going to run or what compressor you're going to run, you also need to make sure it's 100% dry. You want 100% enough, a lot dry air. That's it, as far as compressors go. You got to pick your plasma cutter for what you're going to be working with. At first, for me, it was just a hobby, right? I just wanted a CNC table really bad, just to cut some knickknacks and paddywhacks. But then whenever things got a little bit more serious, I started realizing that I didn't have a machine that had the duty cycle to keep up or had the production rate. It couldn't move as fast. So then that's why I came to the ThermaCut Extra Fire 85. I am only able to get 65 amps out of it because it has a single phase plug. If you get 3-phase, then you have all 85 amps. But still the duty cycle at 65 amps is 100%. So that's good. That's what I want. I want it to be able to keep going and keep trucking and just keep cutting, right? I want it to be able to outwork us. Now we know a little bit more about the size plasma cutter that we want to use, which is going to kind of correlate to the size compressor that we're going to have, which is going to give us enough air, enough dry air to the plasma table itself. Now as far as putting together or assembling your plasma table, whether you had to like the Langmuir that I used to have compared to the fast cut that came put together, you just make sure you get everything set up right, man. Open up those user manuals and study them and make sure everything is up to tip-top shape, everything's connected, you have everything put together as it should be in the manual. Outside of the computer, I feel like 90% of my issues have tracked from this spot right here, as far as either cut quality or error codes. What we're going to look at now is the same thing that we've looked on other videos, is all of these consumables that go into hand when it comes to plasma cutting. Now a few of these consumables are not going to change at all. First off, we'll talk about our swirl ring. All right, this is the ring that just shoves right up on in there, right? And you see them holes there. It directs the air in a certain direction, and it's gonna end up having a clockwise swirl in it. So that's why cut direction in your programming is very important too. We'll get into that later, but that has to do with that swirl ring right there. We'll go in next is your electrode. Now your electrode is important. You want to make sure you have the right amperage electrode for what you're using. We've got an electrode that's 45 amps to 105 amps, so we're good all around for using it. Now, when do you know exactly when they're bad? You'll notice that these electrodes start to have a little bit of pitting on the end of it. Now, I've got a couple of these electrodes that I've gone ahead and swapped out and put a new one on, probably a little prematurely. All of these here seem to be okay. I usually change these when I change the nozzle, but I do think that these electrodes usually lasts a little bit longer than the nozzle. This is another thing that a lot of people don't take care of, and is that O-ring right here. This O-ring needs to be lubricated. So you get some silicone lubricant. You don't need a lot of it. And just make sure that O-ring right there stays lubricated. This is going to help make sure that that doesn't dry out, rots out. And once it goes bad, and again, you don't need a lot. Once that O-ring is nice and lubed up, that's going to help as far as the air quality coming through and make sure that air goes the right direction. Again, with the electrode going in, now we've got to select our nozzle. Now the nozzle size is very important. I've got 85s, 55, 65s, and 45s. The biggest difference with these is the orifice, the hole that's on the end of it, which we should have already talked about in other videos. The biggest thing now is we really don't want to be playing around with that hole size. We want to make sure whatever we're trying to cut and that is programmed in there. If we want to be rocking and rolling at 65 amps, we use the 65 amp consumable. If we're going to be doing 45 amp cuts, we use the 45 amp consumable. Nothing really changes from the hand torch or what you should be doing. The only thing that's a big difference when it comes to these nozzles is the fact that it's a little bit more critical in order to get the cleanest cut all the time. And I think again that electrode is pretty good. I think even though it was slightly used, it'll still be good. That nozzle is actually brand new. The other thing is this right here. I know this is probably one of the smaller nuances to things, but as I go about tightening this retention spot, there's a little gap between that electrode and this nozzle. You can even hear a little bit of bounce in it. If you take away from that and you tighten this down too much, you might get an error code, or it's going to have a bunch of issues and start destroying some consumables. So we want to make sure that when we're going to tightening this retention cap down, you only tighten it to there. I know that sounds silly, but it took me, I can't tell you, days of trying to figure out why I was getting an error code on my plasma cutter. And it's because I didn't have, that was just a little too tight, just a little too snug. Get it to where it starts to be tight with a couple fingers and you're good to go. Now that we got that, we have our shield or shroud. This thing can get boogered up, okay? And if it gets boogered up and it catches some steel, or it's gonna make the contact distance off, a lot of things can come into a big issue as far as your cut quality and making your machine be reading the right voltage if you have a bunch of schmutz on there. So the piece de resistance to getting clean cuts outside of lubricating that O-ring, having the right consumables, not tightening this too much, is a little bit of anti-spatter. Just a little bit right there on the nozzle shield should be plenty, and then we're good to go right here. So if the trend continues, as far as from the other videos of plasma cutting that we've done to this CNC video, the thing that we should be trying to figure out next in order to get the most cleanest cuts possible, travel speed. That's right, travel speed. And where do you start as far as travel speed on a CNC table? Again, it's going to have to refer to your user manual for your plasma cutter itself. So I've taken the PDF online that I found, saved it to my desktop, right? And you'll see here that it has cutting thicknesses for mild steel, stainless steel, and aluminum. Now, we don't have every single type of material thickness on here, but at least it gives you kind of a baseline. And I still would consider thinking about whatever table you have, to whatever compressor you have, whatever plasma cutter you have. These numbers might vary. So depending on the different brands, again, these numbers aren't always the same. But at least it's going to give you a baseline of where to start. If you look, for example, we'll go to something like the mild steel at 12 gauge here. It has your pierce height and your pierce delay time. So we want to make sure our height from our workpiece stays the same. That has to stay the same. Now, a lot of plasma tables nowadays have a torch height control, which is a sensor that senses the voltage of where that material is, and it's able to maintain that height. If you don't have the ability to maintain the height, you'll need to reference your cut chart so that you know how high you need to program in your cam setup in order to get the right height. Your cutting speeds have two different ones as far as your maximum speed and recommended speed. I usually try to stay along the recommended speed if I'm doing a lot of round things or if there's a lot of turns, but if I've got a lot of straight lines and straight pieces, I usually bump it up a little bit. Depends again on what you're running as far as amperage and whatnot. You can see the voltages here as well and your kerf width. Now your kerf width is the amount of material that is removed from the actual cut itself. Now this is going to change depending on your cut speeds and the nozzles that you're running on your consumables. So typically you'll know what your kerf width is depending on what nozzle you're running and what thickness of metal that you're going to be trying to cut on, because that's going to kind of go hand in hand with your cutting speed. Now if these numbers here are subjective to a lot of the other variables in the whole process, how do you know if that's actually right? I wish I had a good answer for you guys. It more or less comes from trial and error. This nice piece of 10 gauge is what I'm going to be using for a project. I'm not going to be practicing trying to figure out my cut speeds on a piece of steel that I'm using for a project. We're going to be using some scraps today. I got some 16 gauge. I got some scrap 10 gauge we're going to try it out on, as well as a little sliver of some 1/4 inch. Might as well. I haven't actually found out the exact cutting speeds to these thicknesses of metal that I normally run in my shop, so I'm excited to find out just how many inches per minute that I can find to get the best cuts out of these steels. Now remember y'all, we have the mechanical things that we need set up properly in order to have a nice clean cut with our CNC plasma table. If you don't have any of those things prior, the good amount of air, the good clean amount of air, the right consumables for the right amperage, that you have that silicone ring nice and lubed up, you have some anti-spatter on it, everything is set up properly before you even get to the computer stuff. Now what I'm going to do in order to go to these cut charts that we just talked about and test to see if they're what I want and that's going to be working for me is I'm going to take away that nice piece of 10 gauge and start doing some practice cuts on these other pieces of drop. So what I've got here is a simple piece. It's a square with a circle in it. I think this is a good test piece in order to see if the plasma cutter is doing what I want without wasting too much material. You could probably add a couple holes in here to make sure that it's tracking properly. I don't do the cam stuff inside Fusion 360. I do the CAD stuff in here. It's just I'm more familiar with it. I was familiar with the cam side of stuff until I got the fast cut table. They're more familiar with the sheet cam side of stuff that had all the tools already built in for me. They actually did the research for Hypertherm and for the Thermacut Extra Fire and found all of the cut speeds for each tool for any type of operation that I wanted to do. Essentially, they put all those cut charts that we just did and put them already in here for me in sheet cam. So for example, if we go to mild steel, we're going to be starting off with 16 gauge, 45 amps. So we look here, we got mild steel, 16 gauge, 45 amps, 139 volts, air. That's the one we're going to do first. It's going to set my feed rate at 278. Now that is pretty much exactly where that cuts chart is going to recommend. So I'm not going to touch that at all. It was about the same, give or take a couple inches. We're going to make sure we have the right offset for our part. That's going to be where the actual part starts to pierce, whether it's inside the circle or outside the circle. Depends on what you're trying to keep, right? What's nice about these machines is they should try to compensate for that swirl ring that we talked about earlier. You're going to notice this direction of cut on here, we have some arrows on the inside. This circle is going counterclockwise as the arrows go, but that's going to make sure that the right side of the plasma torch is on the cutting edge. That's going to lead for a square cut if you are cutting the right direction. Same thing with the outside. It's not going this direction where the torch would be on the left side. It's going to the right to make sure that the material cut is on the right side. But looks like we have everything that we need here. It looks right. We're going to go ahead and post it. What that's going to do is save it so that I can upload it into my Mach 3 controller. I'm going to go ahead and make a bunch of these so that I have different cut speeds for the 16 gauge, for our 10 gauge, and for our 1/4 inch so that we can see some different results. Alright, so now we're going to test it. We got Mach 3 opened up.
45 amp consumables. We're running currently 16 gauge steel, 278 inches per minute. Woo! Straight moving. Now we're going to go 350 inches per minute. Woo! I definitely started seeing a little drag. Now we're going to run 16 gauge, 150, 150.
Alright, so we cut this first one here at kind of more optimal speeds. We can look at the dross on this one. Man, that looks really good. We got some little schmutz in the corners here. The circle is clean as can be. A little bit of dross in the corners there. It looks like a really nice cut. It's hard to tell if anything is cut square on 16 gauge because it's just so thin. This was the 350 inches per minute. I'd say there's significantly less dross on there. Definitely less dross. However, as far as a right angle goes, I feel like these corners got a little bit rounded off a little bit more. It looks like we could potentially pump up the numbers that I'm seeing as far as a 45 amp consumable, 16 gauge, and what the cut chart is telling me. I'm able to go almost 100 inches a minute more and still be able to cut this part. So these are the things that you need to consider. Now looking at this one we cut a lot slower, you should know this from our other videos. If you want a drossy part, you cut slow. This one was cut at still 150 inches per minute. And we still got just so much dross on every inch of this thing.
Alright, next up, we've got the 10 gauge piece of steel. We're running this one at 175 inches per minute. We've got to kick up our amperage. I messed up here, guys. I got to kick up my amperage to 65, and I'm also going to have to change out that electrode to my 65 amp. 10 gauge, test 1, open, run. 175. Alright, second test, 10 gauge, test 2. We're running wide open, 260 inches a minute. Woo! Not good, baby, not good. Oh no! We're going to run test number 3 on the 10 gauge. We're going to run it real slow at 80 inches per minute.
Alright, taking a look-see at these. This is the first test we did, and we're here at 175 inches per minute. Now that dross is, on these straight pieces you can see, is a lot easier. And notice on the sides of this, we got one side with a clean cut, and this dross really is not, I wouldn't say I'm able to just pick it off with just my finger. That's some pretty decent cut action there on some 10 gauge steel. Now we increased the inches per minute far too much. As you saw, that tail and that plasma, it started to go a little bit further behind. Well, here it couldn't even get caught up to get through the plate. You can probably get away with moving a lot faster on thinner metals, but you'll really find out real quick on thicker metals whenever you're moving too quick, because you just won't cut through. I can't get that piece out. This is the piece that we cut a lot slower. It's a little bit warmer, but we cut this one at 80 inches per minute. We've got a significantly kind of a hunk of slag right there, a hunk of dross on the edge of it here, and still not that much dross on here, you know. I could still clean this up very quickly and have a good part. But again, with the heat input being a significant amount more than this one, and there is just a lot less dross compared to the slower and the right on the money and the too fast, we can't even get it out.
All right, now we've got 1/4-inch plate, 65 amps. We're running 85 inches per minute. Not bad. This is where we're really going to see that square cut. This is going to be test number 2. 200 inches per minute on 1/4 inch. This is going to be an absolute mess. Oh yeah. You see that, you got to hit that stop button, baby. Just go ahead and go to 0, go back, go turn everything down, Bubba. We're going to start right here, and then we're going to load the new G code. Too slow, 1/4 inch test 3. We're going to be running at 30 inches per minute. Oh, it's so slow.
I about fell asleep on that last cut. I could see the dross forming on the back side of that. Now, as far as looking at these two here, these are our 2 1/4 inch pieces. This was the appropriate speed that we got from our cut charts, and this was our too slow or slower speed at almost 100 inches per minute slower. This one obviously has less dross on it in a couple spots, but I think the biggest thing that I'm seeing is that square cut being cut into it. This one, the one with more appropriate speed, the edges seem to be a lot squarer than the one with the slower speed. On one side, I've got a little bit of a taper on one side and a little bit of a slope on the side of a circle, which is not exactly what you want if you want perfect circles. But really, guys, I hope this did help as far as trying to target how you can get cleaner cuts with your plasma CNC table. I truly believe that it's 85% of it is setup. You gotta have it set up properly. You gotta have the right consumables. You gotta have everything, that little O-ring lubricated properly. You gotta have everything torqued down properly. A little bit of anti-spatter can help to make those consumables a little bit more happier. And if your consumables are happier, your cuts will be happy. I hope that helps, guys. We'll see y'all on the next weld.